In the last video, we talked about path loss and shadowing, how signals weaken with distance and get blocked by obstacles. But here's something interesting to notice. Even when there's no direct line of sight, your phone still gets a signal. How is that possible? Let's find out. The answer is signals are clever. They find alternate routes. One copy bounces off a building. Another bends over the rooftop. A third scatters off nearby trees. So instead of one signal arriving at your phone, multiple copies arrive, each with a different delay and a different phase. This is called multipath propagation. Now, let us break down the three mechanisms crucial for multipath propagation. First mechanism, reflection. When a signal hits a large, smooth surface like a car, it bounces off, just like light in a mirror. The angle going in equals the angle coming out. Simple. Reflected paths are usually the strongest multipath components. They carry significant energy. Second, diffraction. When a signal hits a sharp edge, like a rooftop or building corner, it bends around it. This is what lets signals reach into shadow zones, places with no direct path. In other words, it enables non-line-of-sight coverage. Third, scattering. When signals hit rough or small objects like trees, they scatter in many directions. Unlike reflection, scattering creates many weak paths instead of one strong one. It's less predictable, but adds to the overall multipath mix. Now, to really understand multipath, we need a tool called the phaser, which is basically a better way to visualize signals. Imagine an arrow rotating in a circle. Its vertical projection traces out the sine wave. The length of the arrow is the amplitude. The angle is the phase. So a phaser captures both amplitude and phase in one simple picture. This will be very useful. Here's something critical. When a signal travels, its phase changes. In the given scenario, initially both the signals are in same phase. Now, as the second receiver moves and signal 2 travels an extra lambda by 4 distance, the phase changes by 90 degrees. And as we keep on increasing the distance, at lambda by 2, the phase equals 180, and the phaser completely flips. Phaser gets back to its original state after a total length of lambda from initial position. These observations shows how even small distance cause big phase changes. We can also summarize these phase changes using a formula. Say, phase at first receiver is 2 pi times d1 by lambda. And if the signal at receiver 2 traveled an extra lambda by 2, the phase is given as follows. On further simplification, we can clearly see that an extra lambda by 2 distance changes the phase exactly by 180 degrees. Now, when multiple signal copies arrive at your phone, what exactly happens? We add their phasers, tip to tail like vectors. The resultant phaser depends on how the individual phases line up. And this is where things get interesting. Let's see 2 extreme cases: constructive and destructive interference. Case 1. Both signals arrive in phase. Their phasers point the same direction. We add them and get a strong resultant, a strong signal. This is constructive interference. Case 2. Signals arrive completely out of phase, 180 degrees apart. The phasers point opposite directions. They cancel out. This gives weak or zero signal. Let us look at this real-world scenario. This describes how your phone signal can drop just by moving a few inches. The phase relationships shift, and suddenly, the signals cancel instead of adding. This is the turbulent characteristic of multipath. Engineers also visualize multipath in the time domain, using something called the power delay profile. On the x-axis, we have delay, when each copy arrives. On the y-axis, power, how strong each copy is. The first arrival is usually the direct or strongest path. Then reflected and scattered copies arrive later. The spread of these arrivals is called delay spread. If it's too large, symbols start overlapping, causing interference. But that's a topic for another video. So far, we've added 2 or 3 phasers. But in a real city environment, you might have dozens of scattered paths, all with random phases. Each phaser points in a random direction. When we add them tip to tail, the resultant is unpredictable. It fluctuates randomly. But this randomness follows a specific pattern, the Rayleigh distribution. Here's what it looks like. Most of the time, you get a moderate signal. But notice this region near 0, deep fades. They happen more often than you'd expect. Now, if there's a strong line-of-sight path along with the scatter, the distribution shifts. This is called Riccian fading. The LOS component stabilizes things. But in pure NLOS, Rayleigh is the model. Many random components, random phases, random amplitude. Deep fades are part of life.